What's up everybody, this is Cakez and welcome back to another tutorial in which we add sound to our game. Finally, first I want you to go into source and create a new file called sound.h. Inside the file we will obviously do a pragma once. We include the schnitzel lib and then we add in sections for constants, structures, globals and functions. I want to start with what a sound is. And for me, a sound is something that holds a file path or a file, options, and then down here the data. For example, what I want to have as an interface in the game is just a function where we say play sound, and then that will take in a file name together with some options. For example, if we want to fade in the sound, if you wanted to fade out, that would stop the sound, for example, or looping the sound is also possible. And that is what these options do at the very top here. You might have noticed that we need a constant in order to complete the sound, and so I'm going to paste in a bunch of constants here. First, the max sound path length needs a little bit of explanation. What I want to do essentially is, when we access the sounds later on, I only want to supply a file name and then we have a predefined path in which we look for. And that would look something like this. For example, if we switch down to the functions, sound functions section, I'm pasting in two functions to play sounds. The first one is going to play a sound using a sound name, a character pointer, and options. And this is the only interface that I want in the game. This will give us control over fading in, fading out, starting and stopping sounds. Because further down below we have the stop sound function that just calls play sound with the fade out option. If we take a look at the interface, I have an assertion at the very top to make sure that we actually have a sound name, and then in the options I check whether I have any options supplied, like for example, are we starting the sound, or maybe we fade in the sound, maybe we fade out the sound. If none of these options apply, then I at least want to start the sound. Then we create a sound on the stack and add the options to the sound. This is where we are going to create the sound, and this is also the reason why this is a character array, because later on we are going to allocate this on the main. We can actually do this already if we want to. Our sound state structure looks something like this. We have an allocated buffer. This will hold all of the sounds that we have loaded from the disk into the game. This one will be quite big. If we go at the very top, you can see that we are allocating 128 megabytes for this. In order to understand why this is so much, I want you to go into the assets folder and then create a new folder below that and call that sounds. Then I want you to go into the file explorer. If you want to get the sounds that we are going to use in this tutorial, then head over to the GitHub page. The link will be in the description. Open up the assets folder there and then switch into sounds. And this is where you will be able to download the WAV files. Once you have all of the sounds here, first steps is the background music of Celeste, and it takes about 40 megabytes to load as a WAV file. WAV file is uncompressed data, in case you're wondering. So if you load more than one background sound and then you keep track of which sounds you have loaded and maybe you unload them, then you can see how we can fill up 128 megabytes quite quickly. So yeah, that is the reason why this is so high. And then at the very top here we have the maximum concurrent sounds. This is just how many sounds we will be able to play at the same time. And then I also have the fade duration, which will come in handy later, but it takes about a second to fade in and fade out the sound. Okay, if we now go to the sound state, then you can see that this allocated buffer, this is the 128 megabytes. We will also have a transient storage to load in sound files and then copy them over into the allocated buffer. Further below we have the amount of allocated sounds that we are currently looking at. Right now we don't have any way of clearing or unallocating the sounds. It's basically the same as a bump allocator. We're just loading in more and more sounds. And then at the very bottom we are going to have an array of playing sounds. This is actually what the play sound function will interact with. For example, we create a sound on the stack, then we add the options to the sound, and then further down below we are going to copy into the file path of the sound the assets sounds WAV file from the very top, the sound name. And this is where these sounds come into play. So if you want to play a sound, we're going to call play sound with, for example, first steps, and then it will fill in the path. So the path is hard-coded and I want to keep it that way. The reason why I hard-code the sounds is because I want to make sure that everything is nicely organized in one folder. And if the folder doesn't exist, then the sounds don't play. Now you might have noticed we need this array size here. This is a macro, and in order to implement that we need to go into the schnitzel lib header file, and then at the very top where the defines are, this is where I want to put it. Array size looks something like this. It takes the size of an array and then it divides by the size of the first element in the array. So essentially what this does is gets a number of bytes. That is the entire size of the array. And this only works for arrays. It does not work for pointers. And then it takes the size of the first element in the array. And if all of the elements have the same size, let's say we have 100 and then the first element is size of 10, then we divide 100 by 10 and therefore we know how many elements we have in the array. That's how the array size works, and if we now switch back to the sound.h file, that one should work. And so yeah, that means we are sprintfing into the sound.file array our sound path. And the reason why that is an array is because of our game.cpp file being separated from our engine. So basically our game DLL will need to have these sounds or access to these sounds, because for example, let's say we are in the game, right, and then when we jump I would like to play a sound, and this is as simple as it looks. It is just a simple play sound function, and in order to actually call this, let's fix this, we have to go into the game.h file, then at the very top we include the sound.h, and then we switch back to the game CPP file and we can access play sound. So this is what it will look like in the game. We will just play the sound jump, but this string is located in memory of the game DLL. So basically the game DLL is a file, and we can locate that right here to the left. This is the file, and inside of this file, this string, what is called a string literal, is allocated. So it resides inside of the DLL. And that means whenever we reload the DLL, the memory location of this string is going to change, which means if our sound state, when we have an array filled with sounds, if they keep track of pointers here that point to game DLL memory and we reload that memory, the pointer will point to garbage, and we don't want that. And this is the reason why this is an array. So now that we know why we sprintf into here, we need to make sure that we actually have a sound state. So in order to do that, obviously we switch to the global section, and you guessed it, we make a pointer. We create a static sound state pointer, sound state. And I think in order to continue, I would like to just connect this to the game and to the engine. So we start off with the game.h. We have the sound header here. At the very bottom in our update game function, we add in the sound state in pointer, and then we switch over from the game.h to the game.cpp file, right where we update the game. That should be at the very bottom somewhere right here. This is where we post in the sound state too, and we obviously have to assign that as well. Okay, now that we have everything in the game, I want you to switch over to the main file and then also include the sound here, and then we also have to fix the game. So below the game.h, include sound.h. And then we scroll down to the main function, and this is where we have to supply the update game with the sound state. We do that here in the main loop, and then we also change the update game function, the wrapper function below the main function, by supplying the sound state in and then supplying that to the update game pointer. Alright, now that we have all of this, we need to actually allocate the sound state. So below the game state, I'm just going to put in code for the sound state allocation. We're going to allocate the sound state, obviously using our BAMP allocator, the persistent storage. If we don't have a sound state, we return an error. And then if we have a sound state, then we want to supply the transient storage as a pointer. We're going to access the same one as everyone else. And then I also want to allocate the buffer for the sounds, you know, the 128 megabytes. And this is where we will run into a problem if at the very top we don't change the 50 megabytes in our persistent storage. I'm just going to do 256 megabytes. You can play around with this value. It is a little bit high. I'm not very happy about this, but at the same time 300 megabytes should be okay, because we are not going to use all of that anyways. Okay, now that we have the allocation done and we are supplying the sound state to the game, it is basically connected now. We need to make sure that it actually works. The play sound function, again, takes in a sound name, looks at the options. If nothing is supplied, it will at least start the sound. Then it creates a sound on the stack. It will sprintf the name and the sound into the sound file path. And then it will loop over all of the allocated sounds in the sound state. And if it finds a sound using the string compare function that is already allocated, we do not want to allocate a new sound, and then we will just use this allocated sound to play it. And how do we play it? Well, we add it to the playing sounds array. And this will come in handy, or in a second important, when we actually add sounds. And we are going to use XAudio2 in Windows. And then further down below, if we did not return by finding a sound, we need to load in a WAV file using our persistent storage and the sounds file path. And now we don't have WAV files, or we don't have any way of loading WAV files. Fortunately, it is actually very simple to load WAV files. And when you use a program like, for example, Audacity, you can take any MP3 file. If you have, I think you need an extension for this, but I'm not 100% sure. You will be able to export most of the audios using WAV files. And then it should give you the proper format that we need, which will be 44,100 Hertz. But for now, we don't even know how to load WAV files. And in order to do that, which is again very simple, we go into the schnitzel lib, the very bottom, and this is where I'll show you how WAV files are structured. A WAV file in general is separated into chunks. These chunks have IDs and a size in bytes. And then below that, the actual data. And we are assuming that we have a riff chunk followed by a format chunk followed by a data chunk. This can be wrong, of course. And the reason why we are assuming these chunks in this order is because this is how Audacity or most WAV files are structured, but not all the time. So you need to make sure that this is the way it works, because otherwise this WAV header is not going to work. You have to make sure that you identify the type of chunk first before you say that, okay, this is a format chunk, this is a data chunk, and this is a riff chunk. And the way you do that is by looking at these IDs. These integer values will tell you what type of chunk you are looking at. And so this is why the header will also display this in this way. The first one is a riff chunk, so that takes in the riff chunk ID. Then it has the size and the format. After that we have the format chunk, which is again, the first thing is an ID. After that we have the size, like always, and then it gives us a bunch of information about the WAV file, the audio format, the number of channels, the sample rate, and all of this stuff. And then at the very bottom we have the data chunk. You might have noticed that this data chunk has a character array instead of an int. It is important to understand that an int in this case is the same size as a character array, and the reason why we are doing this is so that we can actually read, and it should say DATA as a character array for data. And then below that we have the size of the data in the chunk. And this is a WAV file header that we are going to be using in our game. And below that we have the actual WAV file. And the way this is structured is that we first have the header, and then it has a character for the data begin. And I'm going to use this data begin in the sound.h file right here. When we copy over the contents of the WAV file into the sounds data, this is where we use the address of this data begin field. And this makes it very easy to understand, okay, this is the data there begins. It is not a perfect solution, but yeah, it actually works. Quite funny. Okay, and then as the last thing, we have the load WAV file function. It takes in a path, a bump allocator, and then it basically does the read file function. If we have a WAV file, we continue. If we don't have one, we toss an error and return an empty WAV file. Actually, this could be null pointer here, but it doesn't really matter. But if we actually have a WAV file, then we need to make sure that the number of channels and the sample rate, which for us is 2 channels and 44,100, is supported. If not, we are asserting, and then we also compare if the data chunk ID is the same as DATA. And if that is the case, then we return the WAV file and we can use it in the game. Or in this case, in the sound library, where we load in the WAV file in case we didn't find an existing sound to play that is already allocated. We need to load in that WAV file, and if we are able to get that WAV file back, then we need to make sure that the data size, the size of the sound, that's the actual size that we are interested in, is enough to be held in our sound buffer. If we have enough memory left, then we continue. If not, we toss an error, of course, that we exhausted our capacity. But if that is enough, then we set the size of the sound to the data chunk size. We set the data to the memory location of our sound buffer, offset by however many sounds we have already allocated. And then we obviously increase the amount of bytes that we are currently using by the size of the sound. And then we copy over the data from the WAV file into the sounds data. After that, we add the sound not only to the allocated sounds, but also to the playing sounds. And this is everything that the play sound function does. It is a lot of memory management, and I can feel if you find this a little overwhelming or very overwhelming, just try to take your time and look at this and try to understand. But essentially what we have now at this point here is an array of sounds that are already allocated in the system and an array of sounds that we want to play. As you might have noticed, noticed that over here we have not defined the number of channels and the sample rate. And I want to do this in the schnitzel lib at the very top where we have defined, right above here. There is a section called constants, and right now we are just defining the number of channels and sample rate. We have 2 channels and 44,100 as a sample rate. We save this, and then our sound.h file should be fine, and also the schnitzel lib at the very bottom should also be fine. Great, now that we have this, we can unfortunately not play sounds yet. In order to do that, in order to play sounds like this in the game, we need some platform layer that actually handles the sound buffer creation and then the mixing for us. And for us, we will be using XAudio2 because it is a very simple interface in my opinion, and very fast to program actually. Doesn't take many lines of code to set it up. So in order to do that, I want you to switch over to the platform header file because we will need 2 functions. We need to initialize audio and we need to update audio every frame. This is where the playing sounds will be looked at, and you know what we need to add to our sampler or not, stuff like that. Okay, so the init audio function takes in nothing and returns a boolean, and then the update audio function just takes in the delta time. And this delta time is needed because of the fading in and fading out. And so we're going to implement these 2 functions in the Win32 platform layer. So switch over to that and then go to the very bottom. Since we are going to be using XAudio2, you can see that there's a lot of undefined things. I want you to go to the very top. We have to include the XAudio2. Below windows.h, we put in the XAudio2.h header file. Then saving should give us a lot less errors at the very bottom. First, we just have to initialize a multi-threaded. The documentation about the co-initialize.ex function is not quite clear. It basically initializes a COM library by the calling thread, and then it sets the thread's concurrency model and creates a new apartment for the thread if one is required. Now that is not very helpful at all, and the parameters that can be chosen are the co-initialize apartment threaded and the multi-threaded flags. They cannot both be set, but the default one is multi-threaded, which is the one that we apply here. Inspecting the co-init enumeration gives us further info. It basically determines the concurrency model of the incoming calls. What that means is that we have the option between using apartment threading and multi-threading, and those control how incoming calls to any object created by that thread are handled. So for example, in the apartment threading, all incoming calls are serialized because all objects created run on the same thread, aka the apartment/thread that created them, which is the same thread. On the other hand, multi-threading does not give us this. There is no serialization. While this offers the highest performance, of course, we also have to enforce our own concurrency model, which means that we have to make use of semaphores or mutexes, making sure that 2 threads do not write to the same data at the same time. Essentially what we're doing here is we're telling it that it's going to be multi-threaded. When we have this result, we need to check whether it failed or not, and if it didn't, we continue, otherwise we return false. Then after that, we need to get a handle to XAudio2 by calling XAudioCreate. These are mostly initialization functions, and I don't want to go into too much depth on them simply because I'm not qualified enough to talk about them. So this is what we have to call in order to create our XAudio2 structure, and then we create what is called a mastering voice. This mastering voice is a buffer, and in this buffer we can use samples from our sounds, mix them together, and then supply them to this buffer. This is what is the primary buffer of direct sound, for example. And if you want to, you can use this to mix your own sounds together, you know, like create some special mixes, which is what very high-end engines do. In our case, we are just going to use this mastering voice and then a bunch of smaller voices or normal voices that are then being mixed into this mastering voice. In order to do that, we create a wave format structure. This is where the number of channels and the sample rate come into play, and this also the bits per sample. A very quick explanation on what a sound actually is. If we have a table to the left and in the middle is 0, then a sound is just waves that go up and down. And this line can have a minimum and a maximum. And when we say 16 bits is a short, aka has a value range between -32,000 to 32,000. And so then a sound is just a bunch of dots on a line. You can think of it like an extended function. When you take 2 sounds and want to mix them together, you're taking the sample from one sound and add them to the sample of the other sound. That is how you can mix sounds together. XAudio2 will do this for us, but I just wanted to quickly tell you what these values in the wave structure mean. This wave structure is data that the voice needs when we create it. In order to actually create this voice, we have to define our own structure that has specifics tied to Windows. And in order to understand what I'm talking about, I'm going to go to the very top and I need to create a new section here that is the Windows structures. Right below the includes, we have to create a XAudio voice structure that inherits from the XAudio2 voice callback. This is something from Windows and it wants us to implement these functions, or at least some of these functions, but we definitely have to have these functions. And so this is what you are seeing here at the very bottom, these functions right here. But the cool thing is we can also add in our own things. We definitely need the voice. This is the XAudio2 voice, and this one will be sampled into our primary buffer or the mastering voice. Our XAudio2 voice will also hold in the options. These are going to be important later when we update the sounds, so we can look at the voice and see, oh, this one needs to be faded in, this one needs to be faded out. Are we done fading in? Okay, then remove the option. Are we done fading out? Okay, please now stop the actual sound. And so that means we also have to have some sort of timer for each voice to know how long we still have to fade. And then this time, and this is quite funny actually, we're going to use a character pointer to the sound path, because we're going to now reference the array of the sounds as a pointer. And that is okay again, because in the engine this array is not going to go away. This block of memory is allocated in the engine, so we're not going to reload this. And then we have a simple int playing variable that basically tells us, are we playing or are we not playing? Now the two only interesting functions in my opinion is when we are ending and when we are starting. And the only thing we do here is we are stopping the voice when we end, and we set playing to false. When we start, we set playing to true. And then all of the other functions I'm actually not implementing. I do nothing. If you want, you can do some cool stuff, like for example on loop end, on voice error. There's so many things that you can do, but essentially we have to define this structure in order to be able to use it at the very bottom. You can now see that we are able to use this XAudio voice, which is our own voice structure that is a wrapper around the Windows structure, and you can see me index into a voice array. And this is where Windows comes into play again. We have to go to the very top, and then in the Windows global section we add in the array of voices. This goes back to the max concurrent sounds that we have defined in the sound header file. Currently we have 16 of those, and that means we will also create 16 voices. So at the very bottom we are now actually able to use the voice or index into it, get one back, and then we call the create source voice function. This is from Windows and then takes in the actual XAudio voice from the voice. It's a little bit weird that it's called voice, but essentially it takes in this source voice, which is another Windows structure. And you can see that it has the start, stop function and submit source buffer function and flush source buffers functions. These are things that we're going to be calling. And so yeah, it needs to have this voice and we're accessing it here. And then it also wants to have the structure of the WAV file. How does it look? This one is flags. We do not want to have any special flags. You can supply more flags later, but for now this is the simplest scenario. We're supplying a default frequency ratio. Again, I'm not an expert in this field. I've just been using tutorials just like you. The next parameter is the actual callback voice. And what that means is it wants to have our, callback implementation of our voice, which is the reason why we have to extend this here. So it takes this voice here, which is a pointer. And the last two null pointers are again some special handles that we're not going to be using, because you can do some cool stuff, which is, bundle voices together. And then these voices all follow the same volume, and then you can just, let's say, you have sound effects, you turn down the volume slider for sound effects, and then only the voices, only they get their volume reduced, while the other voices, they have their own volume slider. Stuff like that. It's really cool. And then you can see we set the volume on the voice to the music volume, which is another global that we actually set not on the Win platform layer, but actually the global platform layer over here, the platform globals. And for now I'm going to make all of the music 25%, not 100%, it's too loud. Okay, now we're switching back to the Win32 platform, and we should be able to call or have no more errors with platform init audio. And then this function right here, I would like to go into the main and actually call that inside the main below the platform set vertical sync. We call the platform init audio function inside an if check. If we are unable to do so, then we toss an error and we return -1. Then we switch back to the Win32 platform layer, and this is the last function that we have to cover. It is a little big, but we can do it. We loop over all of the playing sounds. This is where the playing sounds come into play. We get ourselves the sound back. We make sure that we actually have size and data on the sound, and then we check the options. Well, are we starting or fading in the sound. If we do so, then we look for a voice that is not playing so that we can play the sound in that voice. And this is the voice array that we're talking about, the global. After we find a voice, we break out of this loop, and then below we just check, well, have we actually found a voice to play? Yes. Then we need to create what is called a XAudio2 buffer. And this buffer holds information about the sound to be played. For example, if you want to loop, where you want the loop to begin, how many times you want to loop, and stuff like that. So basically we set the flags to the end of stream, XAudio end of stream. A quick check on the documentation for this. This one basically means that a voice can have more than one buffer associated with it. And that would be in a queue. And this warning basically says that there cannot be any other buffers in the queue after this buffer. And then this only affects the warning that would otherwise happen when this queue is exhausted of buffers. So basically there is no more buffer to play. Okay, so we set the flags here, and then we set the data. We use the sound size in the audio bytes. Then we set the audio data to the sound data. And then we set the loop count to either 1 or, if we are actually looping, to infinite. This is the max loop count of XAudio2, which is 254, which basically indicates please loop this forever. After that, we use our voice, and then we access the actual Windows voice, the XAudio source voice, and then we call the submit voice buffer on this voice, which takes in our XAudio2 buffer. If we are then able to get a positive result back, we start the voice, we set the sound path of the file, we know this is the pointer to the actual array, we set the options, you know, fading in, fading out, and then we set voice playing to true, which is an interlocked exchange, which means that this is between threads. We make sure that this happens at this point in time, no matter what happens. So this voice playing boolean is set to true. And this comes from Windows, basically means cross threads. Please access this and then change the data. Okay, now that we have playing sounds covered, we also need to make sure that we fade out sounds that we want to fade out. In order to stop sounds, we look for the fade out option. If we have one, we loop over all of the audio sources. If we find one that is not playing and whose sound path is the same as our own path, then we just add the option to fade out the sound. Because further down below, this is where we are going to update our voices. We loop over the entire voice array. We get ourselves the voice pointer back, and then we check, well, does this voice have the fade in option? Yes, it does. Then we increase the fade timer of the voice by delta time up to a maximum of fade duration, which means right now this is 1 second. So that makes sure that whenever we get enough delta time on our fade timer, that the most value that we have is 1 second. 1.0 is going to be the exact value that each of these will land at. And that is very important, because the moment we reach this fade out duration, this 1 second, we want to get rid of the option to fade in, but we don't want to destroy all of the other options that might be in the sound. And then we obviously set the fade timer to 0, and if someone was dumb enough, some clown, set the fade in option and the fade out option, it will make sure that this happens as well. I just noticed I forgot to actually explain how the volume is calculated, but it should be simple. We take the fade timer, which is between 0 and the fade duration, and then we use that to calculate a t value using the fade timer divided by the fade duration. And this t value is going to be between 0 and 1, which is also the value that you have to supply to the set volume function. Yeah, and then we basically do the same thing on fading out. We check for fading out. If we have one, we do a minimum between the timer and the duration. Then we calculate a t value based on 1 minus the original t value. So basically this time we go from 1 down to 0, and this is very important because we want to set the opposite volume, right? We want to start at the music volume and then go down. And then obviously once we have reached the fade duration, we want to cancel out the bit, and then this is getting a little bit more interesting. We want to stop the voice, flush the buffer, and basically this removes the connection from the sound data to the voice. After that, we set the volume back to normal and we set the fade out timer back to 0. Once we are done updating all of the voices, we want to make sure that we clear out the playing sounds count, because we have actually looked at all of the sounds that we want to play, we have added them to the voices, or maybe we didn't, and then we just want to forget about them. I do not want to play a sound delayed, so basically we're just going to reset this all the time. If we didn't manage to play a sound because so many sounds are playing that we can't play the sound, we just don't do it. We forget about it and we move on. If you start to build the program right now, you're going to get a fatal linking error, which means we not only have to include XAudio2 XAudio2, but we also have to link with it. And so I want you to switch over to the build.sh file and then link Olay32. And then you should be able to build. So now when you start the game and you don't hear anything as I do, we need to add this update to the running loop. So basically we have to add the platform update audio to it, and then when we run the game, we should be able to hear the jumping sounds. Which we do, cool. And now I want to do one final touch in the game. When we go to the update game function and we initialize the game, I would like to play a sound. I want to play first steps on a loop. So whenever we start the game now, we should be able to hear first steps. Nice. So it works. Yeah, and this is everything I wanted to do in this tutorial. I hope you enjoyed it. Please leave a like and subscribe for more if you enjoyed. And I'll see you all in the next one. Peace.